let me recall where we are and what we're going to do. So the previous time we discussed some cryptography, and now I want to switch to a completely different topic. The subject for today will be rings. So now you can feel like you're the Lord of the Rings. That's the pure reason for this topic, for being here. Okay, so a ring is an object in mathematics. So as usually, when we just define a new structure, a new object, we need to specify some data and then pose some axioms on this data. So let me start with the definition, describing all the data and then the axioms. So a definition. So I want to define a ring. So in order to define a ring, I need to choose some data. So what are the data? First of all, I want to fix a set. I want to denote the set by the letter R. This is a set. Then I want to fix an operation, which will be denoted by the symbol plus. And I will call this operation addition. And then I need a second operation, which will be denoted by the dot. And I will call this operation multiplication. So this is the data I need. So I need a set and a pair of operations. Okay, now I don't want these operations to be just arbitrary operations on a set. I want them to satisfy some rules. So what are the rules? The rules are the axioms. Well, there are different definitions of a ring. So I will give you one of them. Well, how to say? There are some very general definitions of rings, and there are some very specific types of rings. I will be somewhere in the middle. So first of all, I want the set R with the operation plus to be an abelian group. So there are 4 axioms here, as you may remember. So the plus must be an associative operation. There must be neutral element, which will be called 0. And each element must be invertible with respect to this operation. So for each element, there must be, for each element A, there must be an element minus A. And plus must be a commutative operation. So the order of the sums doesn't matter. So A plus B equals B plus A. So this is the reminder for what it means that this is an abelian group. So these are the properties of the addition. So this axiom says that the addition is good. Now we want to say what are the relations between plus and multiplication, because right now we may even have that the multiplication coincides with addition without any other axioms. So the second axiom explains the relation between addition and multiplication. And the relation is the distributive law. So multiplication must be distributive over addition. Well, this means that A times B plus C equals AB plus AC, and A plus B times C equals A times C plus B times C for all elements A, B, and C from the ring R. So this is the relation between addition and multiplication. And now we want multiplication to be not very bad. So what it means, well, first of all, we want multiplication to be associative. which means that A, B, C, and A, B, C with these parentheses are the same for all elements A, B, C from R. And I will also pose the condition that there is a neutral element for the multiplication. So there is an element which is called 1, such that 1 times A equals A times 1 equals A for all elements of the ring R. So if we have a set with a pair of operations, plus and dot, and these operations satisfy all these axioms, we will say that R with these two operations is a ring.
Oh,
So,
excuse me. Can I ask a question?
Yep.
Shouldn't you also demand like for each element to be invertible in terms of multiplication?
No, this will be a definition of a skew field. But I'll tell you in a second what happens if we add other axioms. Well, actually, in general, the most general definition of a ring is to pose only these two axioms. This is the most general definition of a ring. You have a good addition, and there is this specific relation between addition and multiplication. When you add these axioms, it means that you deal with associative ring. And when you add these axioms, it means that you deal with an associative ring with an identity. But I just want this set of axioms to be called, well, to define a ring. So for us, a ring is just a set with two operations with these four axioms. So here, so let me write it like this. So here, this is R plus and dot is a ring, just by definition. And that's it. So for example, if you take the set of integers with addition and multiplication, this will be a ring. If I require every element with respect to multiplication to have an inverse element, well, then Z is not Z, the set of integers is not a ring. And moreover, there is only one structure where each element with respect to multiplication is invertible, and it consists only of one point, but it's not, this is not an interesting structure. But okay, for now, so this is the definition of a ring. Then I may pose an additional axiom, the axiom number 5, which says that multiplication is commutative. And that is AB equals BA for all elements A and B. In this case, we will say that R is a commutative ring. Oh, and moreover, as with the groups, if we are given a ring, which means we are given these things like set and two operations, we'll simply say that R is a ring, like R is a ring, assuming that, well, this set R has the corresponding operations plus and dot. So you usually just mention the underlying set without mentioning explicitly the operations, assuming that the operations are clear. So in this case, when the multiplication is commutative, we will say that R is a commutative ring. So the properties of the ring, they always refer to the properties of multiplication. And we may also pose an additional axiom, which is axiom number 6. Well, here we will require that every non-zero element of the ring has an inverse. So for every non-zero element of the ring R, there exists an element B such that A times B equals B times A equals 1. So, and also the axiom number 7 saying that the neutral element with respect to multiplication, which is 1, is not the same as the neutral element with respect to addition, which is 0. So 1, 0, and 1 are to be different elements. So if these two axioms are also satisfied, then we will say that R is a field.
May I ask a question?
Yep.
Like I've been thinking about it. Is there really any difference in the definition for the operations for a group? Like there is addition and then there is multiplication. But as far as I can remember, the difference is only in notation. Are there any properties by which we can determine whether the operation is an addition or whether it's a multiplication?
Okay, there are two places where you have difference. Well, first of all, when you take the definition of a ring like this, there is a clear difference between plus and multiplication, because R with the plus is an abelian group, but R with multiplication need not be a group. For example, if you take the set of integers, well, let me go here, and I want to start with to give you several examples. So let me start providing examples. So if you take z plus and dot, then z with the operation plus is an abelian group. But if you take z with multiplication, this is not a group. This is not even a group. So there is no way you can switch these operations. I mean, if you want to deal with the ring, well, here the only option for you to have plus as an addition and and dot as a multiplication with respect to the definition above. So you cannot use dot as a multiplication as an addition, because it doesn't satisfy the required axioms.
Okay, but if we have two operations which do satisfy the axioms,
okay,
which one of them would be what?
Well, this is impossible, and here is the reason why this is impossible. So you may, well, let's go here. So as you can see, well, here we have four properties for addition. Let's see, how many properties do we have for multiplication? Well, first of all, here we have associativity law for multiplication. It's exactly the same as for addition, so there is no difference. Here we're saying that there must be a neutral element for multiplication, so there is no difference either. But when you go here, for addition, every element must be invertible. But for multiplication, you pose these conditions only for non-zero elements. Only non-zero elements are invertible. So this is a huge difference. And the reason why you pose this condition, if you don't assume that, well, if you allow the zero to be invertible, well, this leads to the fact that your ring consists of one element only. So it's impossible to have a ring with two elements or bigger, such that addition and multiplication satisfies the axioms of abelian group. So you will never confuse these two operations because of this property. I mean, I didn't prove anything, but what I'm saying, it's impossible to have a ring where plus and dot are interchangeable. So you will never confuse them.
Okay. May I also ask a related question to, like, a question related to what I asked initially?
Yeah, but before doing that, let me show you another difference. Here is the axiom number 2, and it's not symmetric. Here, you want a specific relation between multiplication and addition. You want the multiplication to be distributive over addition and not the vice versa. So this is the other place where you can distinguish multiplication and addition. You cannot switch plus and dot in this formula. This will never be true.
Well, then let's assume we have a group, basically a set with a certain operation related to it.
Okay.
How do we determine whether this operation, which satisfies all the axioms of that is required by the definition of a group, how do we determine that it's a multiplication or it's an addition? Like we don't go into the ring theory. We just like have a group and we want to know whether the operation is
no.
multiple.
Okay.
Or...
Well, the term multiplication or addition is just a term. It's just a fancy word to call, well, to give a name for your operation. I mean, you may just use the term operation. It doesn't matter which term you use. It's just a word. I mean, the axioms what matters. You may call it addition, you may call it multiplication, you may give a different name, like, I don't know, like flying or something. Like literally, you may call it elephant if you wish. It doesn't matter. But when you have just one operation, it doesn't matter how you call this operation. But when you have a ring, you have two different operations, and you need a way to distinguish them. So you need a way how to call these operations. And it's, well, convenient, first of all, to choose an appropriate notation, which is plus and dot. And second, it's very convenient to call this operation as addition and this operation as multiplication, because for, well, integers or for any other numbers, we just have this notation and we have exactly the same names for these operations. So it's just a way of convenience, like how to call these things.
Well, I see. Thank you.
Okay, no problem. Are there any other questions?
I have another question. Why do we need the seventh axiom?
Oh, this because we want to exclude the only trivial example. Let me show you this trivial example. So that was a natural example, but there is a trivial example. You may take 1 point set. And then for this 1 point set, there is only one map from R times R to R, which takes pair consisting of these only point to the only point. And this is your addition, and this is your multiplication. And this structure satisfies the rules above. So this is a ring. This is a trivial ring. So in this ring, the element star plays the role of the zero element, and it plays the role of the identity element. And this is the only element. So you may check that all the axioms here are satisfied. So this is an example of a bad ring, and we want to avoid this. We don't want this to be a field. So all the axioms for the field are satisfied here, but the seventh one. So we don't, because a lot of things are just not true for this specific case. So we don't want to always mention this in theorems that the result is true for every field except for this one. Instead, we just exclude this thing from the list of fields. So that's the reason for the seventh axiom to be here. Are there any other questions?
I have two questions. Could you repeat, please, why a group with R and multiplication is not a ring? Is not a group.
Why?
Yeah.
Zero. Okay, because with respect to multiplication, not every
I see, because it's in integer numbers, right?
Yeah, integer numbers. Well,
Okay.
even if you take rational numbers, the zero element is not invertible with respect to multiplication.
Yeah, okay, thank you. I thought it was R, not Z. Okay, and one question, we have a invertible, in the axioms, we have an invertible inverse element for multiplication, but we haven't mentioned any inverse element for addition. Yeah.
But here I somehow covered this by this fancy phrase. I told you that R with addition is an abelian group. Here we have 4 axioms.
Yeah, okay, thank you.
Okay, are there any other questions? Okay, so let me proceed with examples. I just want to provide several examples. And as usually, when we deal with rings, when someone wants to define a ring, he must provide a set and a pair of 2 operations. And well, there are a lot of natural examples where people name the set, and after that, it's clear what kind of operations they assume. But for the beginning, I want to explicitly name all the operations. So Well, when we take the real numbers with addition and multiplication, this is a ring, but actually this is even a field. It satisfies all 7 axioms. Then if we take the ring, the set of square matrices, with real, for example, with real coefficients, and use matrix addition and multiplication, then this is a ring. It's not commutative, and not every element is invertible. Then another example is the set of remainders modular n with addition and multiplication modular n. This is also a ring, and this is a commutative ring. So we didn't use all the properties of this structure. We just dealt with Zn with addition specifically. But now, as you can see, we can even add another operation, and the whole structure is a commutative ring. Okay, so there is another example, and this is an example, well, a very specific one. So let's say A is a commutative ring. Like any commutative ring, it may be the field of real numbers, it may be the ring of integer numbers, or whatever. I want to define a ring of polynomials in variable x. So as a set, it's a set of all possible pictures of this form. Where n is a natural number, and all letters A0, AN belong to the commutative ring A, and X is just a symbol on a sheet of paper. So these are just pictures. So they do not have any other sense. So each picture is called a polynomial. So just a picture. Now, when we have the set of these pictures, well, a bit later I will explain why do I treat the polynomials as pictures and not as functions. You will see the reason, but before doing that, I want to explain how to define the operations here. Well, it's clear how to do that. You just use the usual operations. So if you want to add 2 polynomials together, you just add them coefficient-wise. And if you want to multiply 2 polynomials together, you just use this formula where AK times BM, sum through all K plus M equals D, and then sum for all D, X to the D. So these are just definitions for how to produce new pictures on the right using 2 pictures on the left. So these 2 rules define how to add and multiply your polynomials. So, well, now you may consider polynomials like z3 of x, or even like r of x, or anything else. You may use any commutative ring R, A here. So why am I saying that a polynomial is a picture? Well, you see, if you have a polynomial, let's say a polynomial from a ring like this, so that is, let's say F is this picture, you may define a function, let's say f hat, from A to A. And the function is given by the rule, you take an element A and take this element to f of a, which is by definition is a 0 plus a1 times a plus etc. plus an times a to the n. And you may compute the result on the right because it's an element of a ring and all the operations are well defined. So each polynomial defines a function, but different polynomials may define exactly the same functions. So if you, well, so let me show you an example. Well, for example, if you take z2 of x and you take two polynomials, first of all, f of x to be x and the second one g to be x squared. These are completely different polynomials because they are represented by different pictures. But if you define a map from z2 to z2 by the rule x, well, let's say a goes to f of a, then this map coincides with the map defined by the rule a goes to g of a, because, well, here you have only two elements, 0 and 1. When you apply f to 0, it goes to 0. And when you apply g to 0, it goes to 0. And if you apply f to 1, it goes to 1. And if you apply g to 1, it goes to 1. So the functions f hat and g hat, they are the same. But these are two different polynomials. So when you deal with finite rings, like here, consisting of finitely many elements, it may happen that different pictures give you exactly the same functions. But you want to distinguish the pictures, not the functions. So that's why when you, well, an abstract definition of a polynomial is that the polynomial is a picture and it completely determined by its coefficients. So two polynomials are the same if and only if all coefficients are the same. So it's easier to deal with, and you don't need to worry about substituting test elements instead of x. So just compare the coefficients, and that's enough. So this is how you deal with polynomials in algebra. So are there any questions related to this example? Okay, so let's go on. The next definition is the definition of a subring. Now, when we dealt with groups, when we define groups, we define several other objects like subgroup or normal subgroup. And a subgroup, well, so now I want to, well, a subgroup was kind of a sub-object. So here again, if we define a ring, we want to define a subring that would be a kind of a sub-object inside of a ring. So let me give you a definition. Suppose R is a ring. Let's say R plus and dot is a ring. I want to define a subring. So first of all, as a data, subring is a subset. Satisfying the following axioms. First of all, T plus must be an abelian subgroup of R plus. Well, is a subgroup. Will be automatically abelian because the addition is commutative. But then the second rule, T must be closed under multiplication. So if x and y are elements of T, then x times y must be also inside of T. And the third rule, the neutral, the identity element of R must be inside of T. So if all these properties are satisfied, then T is called a subring. So this is a kind of a sub-object inside of our ring. And so let me give you several examples. In example number 1, Well, if you take the set of integers inside of the set of rational numbers, then this is a subring. If you take the set of rational numbers inside of real numbers, this is a subring. If you take diagonal matrices, let's say this is the set of all diagonal matrices, then this is a subring in the ring of all matrices. So these are examples of a subring. And one additional remark, if you have a subring, then you see you may restrict the addition to the subset. So, well, what is a subring? So it's a subset, and what kind of properties does it satisfy? Well, it's closed under addition, it's closed under multiplication. Well, it satisfies some properties. I mean, it must be a subgroup with respect to addition, and it contains the identity element of the ring R. So, as you can see, when you consider T with this addition and the multiplication from the ring R, it will be a ring with respect to the same operations. So if T is a subring, then when you restrict the operations plus and dot to the subring, you will get a ring again, because it will satisfy all the axioms. Okay. Now, well, if we want to study rings, there are different approaches how to study a ring. And the approach number one is an element-wise approach, when you discuss what kind of elements are there in the ring. And the second approach uses what's called ideals. So let's start with the element-wise approach and discuss what kind of elements are there in the ring. And then we will discuss a more advanced technique. So first of all, the elements of rings. So let's try to classify what kind of elements do we have. So suppose R is a ring. So, okay, so now if we have an element X in R, we will say that it's invertible if it's invertible with respect to multiplication. We say that it's invertible if it's invertible with respect to multiplication. Well, let me say that there exists X inverse, such that X times X inverse equals X inverse times X equals 1. And the set of all invertible elements will be denoted by R star. This is the set of all invertible elements. Well, just in case, the set of all invertible elements with operation multiplication is a group. One may check that if we exclude non-invertible elements from the ring and we exclude the addition, then we will have a group. Not necessarily a Billion group, but a group. Because just by definition, every element here is invertible with respect to multiplication. And that was the only property that we lack when we define the properties of multiplication on the ring. And as you remember, we had this notation for the remainders, Zn star. Well, if you treat Zn as a ring, then Zn star is the set of invertible elements of this ring. That was exactly the same notation as here. And that's not a coincidence. Now, the second thing, a notion of a zero divisor. Suppose we have an element X of ring R. We say that X is a left zero divisor. if there exists a non-zero y such that x times y equals 0. So when we say left zero divisor, we mean that our element is on the left side of this equality. So what does it mean that we have a left zero divisor? It means that we may find a non-zero element y such that multiplying on the right by this element y, we will get a zero result. Just in case the zero element is treated to be a left zero divisor. So if x is equal to 0, it's also a zero divisor. So it's a trivial zero divisor, but it's a zero divisor. So it's interesting to discuss non-zero zero divisors. Well, in a similar way, we may define a right zero divisor. Well, I believe you can do this without me, but I want to fix a notation. So the set of all left zero divisors will be denoted like this. This is the set of all left zero divisors. And dr of R capital is the set of right zero divisors. And left and right zero divisors give you the set of all zero divisors. So when you say that x is a zero divisor, it means it's either left or right zero divisor. So, and if your ring is commutative, then there is no difference between left and right zero divisors. Okay.
Oh, excuse me, but wouldn't that make this or the set of all zero divisors basically just the set of the invertible elements of this group?
Again, the set of all zero divisors, what?
Wouldn't it make it equal to the set of all invertible elements in this group, basically to R star itself?
No. You see, if your element is invertible, then it's not a zero divisor. Why? You see, if you have an equality like this, and suppose that x is invertible, you may multiply it by x inverse on the left, and from that it follows that y is equal to 0. But y wasn't equal to 0 here, so it's a contradiction. So an invertible element is never a zero divisor. I'll show you in a moment the relationship between all the classes of the elements, but I just want to define the classes of these elements before drawing a picture, okay?
Okay, thank you.
So the next class of elements is the set of nilpotent elements. So suppose x is an element of R, we say it's a nilpotent, x is nilpotent, or nilpotent element if there exists a natural n such that x to the n is equal to 0. So if you multiply x several times and you will get 0, then x is called nilpotent. So you will probably know the examples from the ring of matrices. So there are matrices which are not 0, but if you raise them to a power, you will get a 0. And the set of all nilpotent elements will be denoted by nil of R. So this all nilpotent elements. So we'll say nilpotent. And the last but not least is the class of idempotents. We will say that x from the ring R is idempotent if x squared equals x, and E of R is the set of all nilpotents, idempotents. So let me show you a general situation how these elements are related. So if you have a ring R, So this is the underlying set of the ring R. So here is an element 0, let's say. And here is an element 1. Then the set of all invertible elements is somewhere here. So everything outside of this part of the ring are just non-invertible elements. So all the points outside here are non-invertible. Now, the set of all zero divisors is here. So it doesn't intersect the set of all invertible elements. And also, they do not cover the whole ring. It may happen that an element is not a zero divisor, but it's not invertible. For example, if you take the ring of integers, then every non-zero integer is here. It's not if it's not 1 or minus 1. Well, almost every integer is here in between these sets. And the set of nilpotent elements is located here inside the set of zero divisors. Well, the idempotent elements, they intersect all these sets. So then I don't want to draw them on this picture, but so this is what you should understand regarding well, the general situation, how these elements look like how they relate to each other. And let me give you several examples. Well, an example.
Can I just ask a question? Yep. What is a nilpotent element? Well,
it's an element such that there is a power, and rising to this power, you will get 0 for this element. So the element, well, it may be, the x itself could be 0, but if it's not 0, you may multiply it several times by itself, and you will get 0. Then x is called nilpotent. For example, let me show you an example. So you may take a matrix like this in a ring like this. This is your x, and this is your r. Then if you take the second power of x, you will get a 0 matrix. So x is nilpotent. So this is an example for nilpotent element. Are there any other questions? Okay, so well, if you take the ring of integers, then the invertible elements are just plus minus 1. The zero divisors, well, this set consists of the 0 element only. Well, the nilpotent elements of Z, well, there is only the 0 element, and the idempotent elements of Z are just 0 and 1. So this is how all these classes of elements look like here. Well, in case of a ring of square matrices, well, it's easy to define, to describe invertible elements. This is just the set of all non-degenerate matrices. This is the set of all matrices with non-zero determinant. And actually, every matrix with zero determinant is a zero divisor. The set of all zero divisors of this ring actually is the set of all degenerate matrices. Because if your matrix has zero determinant, you may always find a matrix B such that A times B equals 0, and B is not 0. So this is what happens with invertible elements and zero divisors in case of square matrices. Well, I don't want to describe nilpotent elements and idempotent elements because you need your normal form, but let's skip this question here. So, but these are examples. Now, I want to switch to a different oh, by the way, are there any questions? Okay, so let me summarize what happened here. So I described 4 classes of elements: invertible, zero divisors, nilpotent, and idempotent elements. And I described how they're related to each other. Now I want to switch to a different subject. I want to discuss a way how to deal with the rings in a non-element-wise fashion. What can we do with rings? Well, we want to consider subsets with specific properties, and we want to deal with these specific subsets instead of specific elements of a ring. Well, we already know one class of specific subsets is a class of subrings, but this class is not big enough. Instead, we will consider a different class of subsets, and these subsets will be called ideals. And it happens that ideals, well, they describe a ring very well. So a lot of properties can be extracted from the knowledge about the ideals of a ring. So ideals. Okay, first of all, definition. Suppose we have a ring. Now I want, well, I want to define an ideal. Well, actually, there are 3 definitions. There is a definition of a left ideal, there is a definition of a right ideal, and there is a definition of a double-sided ideal, which is just which is called ideal without specifying left or right ideal. So I will give you 3 definitions at the same time. So I want to define a left ideal, a right ideal, and just an ideal. So first of all, as a data, this must be a subset of R. Then we want to pose the axioms. So what are the axioms? Axiom number 1 says that I plus must be a subgroup in R plus. So this is similar to being a subring. And then, well, let's say we want to define a left ideal. We want to say that for each element x of the ring R and each element y of the ideal I, x times y belongs to I. So if you take an arbitrary element from, so if you multiply your ideal on the right by any element of the ring, you will stay inside the ideal I. So the definition of a right ideal is similar for every element x of the ring and every element y of the I. The product y times x is inside the ideal I. So if you multiply on the right by any element of the ring, you will stay inside the ideal. And it's called ideal. So this was left ideal and right ideal, and you'll say that you're a double-sided ideal or just ideal if it's left and right ideal. So these 2 properties hold. So this is the definition of an ideal. I'll show you examples in a minute, but let me point a crucial difference between ideals and rings and subrings. Well, the first part of the definition here and here, you can see, is exactly the same. A subring is an abelian subgroup and an ideal is an abelian subgroup. But in case of a subring, the property for the multiplication is weaker. You just want the subset T to be closed under multiplication. When you take elements inside the subset T, the product must stay in T. But here you want to have more. If you take one element from I and one element from R, you want the product to be in I. So this one is stronger than this one. But in contrast, here we have additional property. We want the identity element to be inside the subring. And here we have no such an assumption. These are technical differences. Okay, so what are examples? But before going to examples, are there any questions related to the definition, just in case? Okay, so then let me give you several examples. Okay, the example number one, if we take Z plus and dot, so the ring of integers, well, then we know that all the subgroups with respect to addition are of the form n times z. Well, it happens that all these subgroups are ideals. So there are no other ideals here. So these are all ideals of z. Let's try to find all possible subrings of z. Well, if we have a subring of z, it must contain the element 1, but because it must be closed under addition and subtraction, we will have 1, 2, 3, and also -1, -2, -3. So we must have all possible integer elements. So every subring coincides with D. So we have only one subring, which is the whole ring. And we have a lot of ideals. So these are all possible ideals, and this is the only subring. So this is what happens here. Another example, if we take the ring of square matrices with real coefficients, then let's take this, the set. Well, I'm not describing all possible ideals, but I just want to give an example of an ideal. So if we take, let's take just two by two matrices for simplicity, and consider all matrices of this form. They have the first column of these matrices must be 0, and the second column consists of any numbers. Then, if you multiply a matrix of this form by a matrix, by any matrix on the left, so if you take A, B, C, D times 0, 0, star, star, the result will be of the form 0, 0, star, star. So this subset is closed under addition, and it's closed under multiplication by any matrix on the left. But it's not closed by a multiplication on the right. So this is an example of a left ideal. An example of a right ideal is similar. You just take all the matrices with 0 row. This is an example of a right ideal. Okay. And let me formulate the claim I mentioned. I just want it to be here. So if we take the ring of integers, and then every ideal, so well, and suppose I is an ideal of Z. When I want to say that a subset is an ideal, I usually use this triangle symbol. So this symbol means that I is an ideal. This is just a notation, a convenient one. So suppose that we have an ideal of Z, then I is of the form n times Z. I have already mentioned that this is obvious because we know that every subgroup has this form. It's clear that this subgroup satisfies the property, and we need to show that first of all, okay, let's do it like this. So we need to show that every subgroup of this form is an ideal, and then we are done, because there are no other subgroups, because these are all possible subgroups. So the only thing that we need to check here that NZ satisfies the second axiom. But what is the second axiom? The second axiom says that if you take an arbitrary integer and you take an arbitrary element here, which means that B is divisible by n, then the product n times A times B is divisible by n. But yes, it's divisible by n because of this equality. So every subset of this form satisfies the second axiom. The first axiom is clear because we already know that this is a subgroup. So this is an ideal. And since these are all possible subgroups, these are all possible ideals. There is a similar claim for the ring of remainders. Remainders. I always pronounce this word incorrectly. Zn plus and dot. So, and if we have an ideal here, then there is an integer, a positive integer k dividing n, such that I is equal to, let's say, let's write it like this, k times Zn. So every ideal of the ring of remainders is of this form. So it's generated by an integer dividing n. Well, I didn't prove this on the lecture, but during a seminar session, I proved that all the subgroups are of this form. But so let me do it here. So suppose we have an ideal here. Well, there are two options. Either, well, since I must be a subgroup, it always contains the zero element. So there are two options. Either there is only zero element, so I consists of zero element only, or there is a non-zero element inside I. If I will consist of the zero element only, then I is represented as n times Zn, or just 0 times Zn, if you wish. So it's just the same. So the claim is true. So this is what exactly happens here. And if we have x, if we have a non-zero x inside I, we want to show that in this case, I is of this form for some non-zero k dividing n. So, okay, well, let's take the minimal possible non-zero x inside y. So let's k to be an element of I, which is not zero and the smallest possible. Then if you take an arbitrary element h from I, you may divide it with the remainder by k, so you can write it like this. So now we may consider this as follows. So this element is an element of I. This is also an element of I. And this is an element of your ring Z. If you multiply an arbitrary element of the ring Z with an element of an ideal, then the result may stay inside the ideal. So, and then if you subtract qk from H, the result also must be inside the ideal because I is a subgroup with respect to addition. So this simply means that the element R is also inside the ideal. But by the definition of the division with the remainder, R must be strictly smaller than K, and K was the smallest possible non-zero element in I. So the only option for R is R to be 0 because of this. So this simply means that every element of I is divisible by K, so that means that I is of the form K times Zn. So as you can see, every ideal of the ring Zn is of this form. Well, and it's clear that for every K with this property, this is an ideal. And by the way, you may take, okay, so I'll give this remark a bit later. Okay, I'll probably, okay. So now we know all possible ideals of the ring Z and all possible ideals of the ring Zn. Well, the ideals will help us to deal with homomorphisms, actually. So let's discuss the homomorphisms for rings. So the homomorphisms is the way to compare different rings. So what is a homomorphism? Of rings. Well, homomorphisms and isomorphisms. So suppose we have two rings. So let me say a definition. Suppose we have two rings, R plus dot and S plus dot. Then a homomorphism is a map. So I want to define a homomorphism from R to S. So as a data, phi is a map from the set R to the set S. Well, this simply means that it takes each element of R to an element of X, of S. So it's a well-defined map, a function, if you wish. And now we have the axioms. The axiom number 1 says that phi preserves the addition. For all elements A and B from R. The second property, phi preserves the multiplication. For all elements A and B of R. And a third property says that phi preserves the identity element. So the identity element of the ring R goes to the identity element of the ring S. So this is the definition of a homomorphism. This is not the most general definition, but this is the definition we will be using. If additionally we have a fourth property, so this means that phi is a homomorphism. Oh, let's do it like this. Oops. Phi is a homomorphism. And if additionally we have a fourth property which says that phi is bijective, then we say that phi is an isomorphism. So this is the definition of an isomorphism. So, roughly speaking, a homomorphism is a map between two rings preserving all the possible operations, and it also preserves the identity element. Well, we know that if we have a homomorphism of abelian groups, and the property number 1 says that phi must be a homomorphism of abelian groups. Well, if we forget the multiplication on both rings, then R plus and S plus are abelian groups, and the property number 1 says that this is a homomorphism of abelian groups, of these abelian groups. And we know that if we have a homomorphism of groups, then it automatically takes a neutral element to a neutral element. So the neutral element for the addition is 0, so the 0 of R must go to the zero of S. But this doesn't happen automatically for the identity element of the rings. So we need to pose this condition additionally. So if you exclude this property from here, it may fail to be satisfied. Okay, so what is, how to understand the isomorphism of rings? Well, if you have a pair of rings, let's say R and S as above, an isomorphism is a bijection, let's do it like that, is a bijection. Well, what does it mean that you have a bijection? It means that the underlying sets R and S are the same. And this bijection preserves the operations. So this simply means that if you take two elements here, you may map them to S and then apply the operations. For example, addition or multiplication. Or you may do it in an opposite, the other way around. You may take addition of the elements here and the sum of elements here and multiplication and product of the elements here, and then map them to the set S. And the axiom says that it doesn't matter which order you choose, the result will be the same. Well, this simply means that not only the underlying sets are the same, but the operations given on these sets are the same, which means that these two rings are essentially the same. So there is no difference which ring you want to study. So if you have two rings and an isomorphism between them, so there is no differences between these two rings. So they are actually the same. They're naturally the same. So this is the meaning of the isomorphism. And if you have an isomorphism between two rings, so if there exists phi from R to S, an isomorphism, you will say that R and S are isomorphic. So isomorphic rings are, roughly speaking, the same rings, but presented in a different way. So let me give you an example of a homomorphism. Well, if an example, well, we can take Z and Zn with addition and with the usual operations, and the map taking K to K modular N is a homomorphism of rings. Then you may take another example. Let's say R and square matrices with coefficients in R. And we have a map taking each element lambda to a scalar matrix lambda times E, where E is the identity matrix. This is also a homomorphism. Then there is another example, example number 3. We can take the ring of polynomials with real coefficients and a field of complex numbers. Then there is a map taking each polynomial f of x to its value at imaginary unit, f of I, where I square equals -1. This is also a homomorphism. So these are different examples of homomorphisms.
Sorry, can I ask a question?
Yep.
So if we have a map, we proven that we have a homomorphism?
No, you need to check that this map satisfies all the axioms here. So you need to check all the axioms. What I'm saying here that you can check that all 3 axioms are satisfied in all 3 cases. So this map preserves addition, multiplication, and the identity goes to the identity. This map also preserves the addition, multiplication, and the identity goes to the identity. Well, this is more or less obvious here, but it should be clear that you need to check all these properties. I'm skipping this verification here. I'm just claiming that these maps are homomorphisms. But if you provide like an arbitrary map, well, with probability 1, it's not a homomorphism, it's just a map. Okay?
Thank you.
So another example, well, let me recall the Chinese remainder theorem in a different way. A claim, well, if we have two co-prime integers, m and n, we have this map phi from zmn to zm times zn. Well, as you can see, the left-hand side is a ring and the right-hand side is also a ring, where addition and multiplication is just a coordinate-wise addition and coordinate-wise multiplication. Then, and the map is given by the rule k modular m, k modular n. We already know that this map is a bijection and it preserves addition and actually multiplication. So this is actually an isomorphism of rings. And not just groups. So this is a bijection preserving addition, multiplication, and the identity element goes to the identity element. So we have already proven all of this, but I just want to summarize and reformulate what we know in terms of rings. So this is the full version of the Chinese remainder theorem. So this is an isomorphism of rings and not just an isomorphism of groups. Okay, and now I want to give you several definitions. Oh, I think we should go up. Yeah. So today we just mostly focused on the definitions and some basic properties and do not probe anything interesting. So suppose that we have a homomorphism from a ring to a ring. So these guys are rings, and this guy is a homomorphism of rings. Then I want to define two subsets. The kernel of a homomorphism. The kernel of the homomorphism is the set of elements of the right ring going to 0, or of the left ring, I mean, of the source. And the image is the set, well, it's just a set theoretical image. The set of elements of this form where X belongs to R. So these guys are called the kernel and the image of the homomorphism phi. So well, if we have this picture, so the kernel belongs to the left-hand side and the image belongs to the right-hand side. And let me formulate the claim regarding the kernel and the image. And this will be the last claim for today. Well, for any ring homomorphism, we have, first of all, the kernel is an ideal of R. The image is a subring of S. The map is injective if and only if the kernel consists of the zero element only. And the map is surjective if and only if the image coincides with the whole ring S. So these are the properties of the kernel and the image. So as usually, the kernel is something to control injectivity, and the image is something to control subjectivity. And the property number 4 is obvious. It's just by definition. I just want it to be here. I just want to pay your attention. Well, I just want to draw your attention to this statement. So, so let's check all these properties. But before doing that, are there any questions regarding the definitions or the claim itself? Okay, I have 4 minutes. I believe that this is enough for this kind of claim. Well, let's see what we have. We have a homomorphism of rings. If I forget about multiplication, this will be a homomorphism of abelian groups. I mean, when you consider R plus and S plus, so this is a homomorphism of these abelian groups. But then just by definition, the kernel, from the definition above, is just the kernel of this homomorphism of abelian groups. So we know that kernel with the addition is a subgroup because of the corresponding result for the homomorphism of abelian groups. I mean, of groups. It's a normal subgroup, but since here everything is abelian, then every subgroup is normal, so it doesn't matter. So this is a subgroup. So the only thing that we need to check that it satisfies the second axiom of the definition for the ideal. So this was the first axiom. It must be a subgroup inside of R. So the second axiom, in order to check the second axiom, we need to take an arbitrary element X from the kernel. We need to take an arbitrary element Y from the ring R, and we want to show that X times Y is in the kernel, and Y times X is in the kernel. So this is what we want to check. But how do we check this? Well, how to check that something is inside the kernel? We need to apply phi, and if the result is 0, then this is inside the kernel. So we need to check if phi of xy is equal to 0. But by the definition, since phi is a homomorphism, it preserves the multiplication. But then phi of x is equal to 0. So we have 0 times phi of y. So now we need to show that if we multiply 0 by anything, we will get 0. Let's do this. So how do we prove that if we multiply something by 0, we will get 0? So let's take s times 0. This is exactly the same as s times 0 plus 0. This is because of the definition of 0. 0 plus 0 must be 0 because it's neutral for the addition. And then because of distributivity law, this is exactly the same as this. And now we may cancel out one summon. And subtracting this red element, we will get 0 equals s times 0. So for any element s, if we multiply this, well, here s was from the ring S capital. So if we multiply by 0 any element of a ring, we will get 0. So as you can see, so if we multiply an element of a kernel by any other element, we will stay inside the kernel. This is exactly the definition of an ideal. So the item number 2, again, if we take an image of phi, because phi is a homomorphism of abelian group, then the image of phi is a subgroup, because phi is a homomorphism of abelian groups. So we need to check that the image of phi is closed under multiplication. What does it mean? It means that if we take an element A and element B from the image of phi, then the product is also in the image of phi. This is what we want to check. And then And we also want to check that the identity element of S is in the image of phi. So these are two properties that we need to check for the image of phi to be a subgroup or to be a subring. Well, the second one is simple because one of S is phi of 1 of R because of the definition, and this is inside the image of phi. So this is how you prove this. But how do you prove the first one? Well, A must be phi of X for some element, B must be phi of Y for some element, X and Y are inside of R. Then, if you multiply A and B, you will get phi of X times phi of Y, because phi is a homomorphism. This is phi of XY, and this is also inside the image of phi. So that's why the first one is true. So all the axioms of a subring are satisfied. So image of phi is a subring of S. And yeah, I see I have like -2 minutes, but I just need like 1 minute more. And the third property, well, if we want to prove that this map, we want to prove that this map is injective if and only if the kernel consists of the zero element only. Well, this map is injective. Well, okay, so since this map is a homomorphism of rings, this map is also a homomorphism of abelian groups, as I already mentioned. And the kernel of this homomorphism, when we consider it as a homomorphism of groups, is exactly the same as the kernel when we consider phi as a homomorphism of rings. But when we consider a homomorphism of abelian groups, it's injective if and only if the kernel of the homomorphism consists of the zero element only. So now the claim follows from the corresponding claim for abelian groups. So for abelian groups, we know that phi is injective if and only if the kernel of phi consists of the zero element only. And the fourth property is just trivial, just by definition. And that's it. So are there any questions regarding the proof or the whole lecture? Justin, by the way, who thinks that he can follow the whole lecture? Who followed?
Sort of.
Okay. Okay. At least some of you could. Not bad. So again, are there any questions? Like any kind of questions?
Yeah, actually, like if I didn't follow the entire lecture, like
Okay.
could you just briefly go over everything?
Oh, okay, no problem. Let me give you a quick overview of what happened here. So I started with a definition of a new object, which is a ring. Roughly speaking, well, a group was a simplest possible algebraic structure. It was a set with one operation. A ring is the second, well, next, more, well, how to say, it's well, it's another structure where you have a set and a pair of operations related to each other. So this is a ring, a set with two operations. And now we discussed what kind of things we can do with rings. So first of all, I gave you several examples of rings. Then we discussed subrings. We discussed specific elements inside the ring, like invertible, zero divisors, nilpotent and idempotent elements. Then we discussed ideals. These are special subsets. And we described ideals of the ring of integers and the ring of remainders. Then I introduced you the notion of a homomorphism and an isomorphism. An isomorphism is a way of saying that two rings are the same. And then I discussed the kernel and the image of a homomorphism and discuss the properties of the kernel and the image, that the kernel is an ideal and image is a subring, and that injectivity can be checked using kernel and surjectivity using the image. So this is everything what happened during the lecture.
Okay, then I have a question about
Okay.
when you when you started discussing homomorphisms and everything. I didn't really, yeah. I didn't
What kind
really
of
pay
question?
attention. Like,
should I repeat something here or what?
Yeah, like basically from where you give the definition.
Okay. So let me repeat the definition. So what is a homomorphism between two rings? When you're given two rings R and S, a homomorphism is a map from one ring to another one, and this map is compatible with the ring structure. What does it mean? It means that it preserves the addition, it preserves the multiplication, and it preserves the identity element. So the definition is basically the same as it was for the groups. So what was a homomorphism of groups? Homomorphism of groups, it was a map between groups preserving the group structure, which means it preserves an operation. So this is exactly the same definition. And isomorphism is a bijection, which is a homomorphism. Well, and here we have several examples of a homomorphism. For example, when you take from Z to Zn, taking each k to k modular n, or you may take R to matrices, square matrices with coefficients in R, taking each lambda to lambda times E, where E is the identity matrix. It's also a homomorphism. I didn't check the properties. I'm just saying that this map satisfies all three properties of the homomorphism. Or you may take another homomorphism, which takes R of x to the field of complex numbers, where you take an arbitrary polynomial f of x and substitute I instead of x. So this will be also a homomorphism from R of x to C. Now these are examples of homomorphisms. And I even reformulated the Chinese remainder theorem in the form that this map is not just a bijection, which is an isomorphism of abelian groups, but this is a bijection, which is an isomorphism of rings. So it preserves addition, multiplication, and the identity element. We have already checked that property, but I just want to clarify that this means that this is an isomorphism of rings and not just abelian groups. So that's what happened here. Is that the kind of words you wanted to hear?
Yes.
Okay, should I do the same with the kernel and the image?
Yes.
Okay, so now when you have a homomorphism from one ring to another ring, you can define two subsets, one inside R, another inside S. The kernel is a subset inside R. This is the set of elements going to 0 in S. And the image is the set of elements here coming from R. So these are elements phi of x, where x go through all the elements of R. So, and here is a brief picture. And now I can formulate 4 properties. First of all, the kernel is not just an arbitrary subset, it's an ideal of R. And the reason why we need ideals, because kernels of homomorphisms and ideals are basically the same thing. So here we prove that every kernel is an ideal, but actually if you have an arbitrary ideal, you can always find a homomorphism such that this ideal is the kernel for this specific homomorphism. So it's always possible to find a homomorphism for an ideal, making this ideal the kernel of this homomorphism. Then the next property, the image must be always a subring of S. It's not just an arbitrary subset, it's a subring. And then how to check injectivity and surjectivity? Well, injectivity can be checked in terms of the kernel. The kernel consists of the 0 element if and only if phi is injective, and we are surjective if and only if the image is the whole ring S. And then there was a proof of all these properties. Should I go through all of them? Or are there any other questions?
So I don't really understand like the line. There is like R implies S and
there are some problems with the sound. I cannot hear you.
Can you hear me now?
Yep.
So I wanted to ask, like, the moment where we have R implies S and the kernel of Phi is a subset of R and image of Phi is a subset of S.
This, you mean the proof of this claim?
Not really. Yeah, it's like before the claim.
Okay, so the definition here.
Yeah. Yes. So like I don't really understand. So
What happens here?
Yeah, I don't really understand why we have like kernel Phi is a subset of R.
Okay,
And,
first of all, what is Phi? Phi is a map. So it's a
Yeah.
rule, taking elements from here and to some elements from here. And what are rings? A ring is a bag. It's a set of elements, which means it is a bag of elements. So there are some elements there. And you also may add and multiply these elements together.
yeah, now I understand.
Okay.
I just thought that image of this mapping is some kind of inverse logic to kernel of this mapping, but now I understand that it's not the case. Also, can I ask about the proof for ideals? I couldn't really get it.
Okay, which one? The ideals of Zn?
So there you have a proof, yes. Like for claim of Zn, yeah.
Okay.
This one, yes.
Okay, so so first of all, what am I doing here? Well, I'm trying to show that each ideal of Zn is of this form. So let's take an arbitrary ideal. So it's a subset of Zn with all those fancy axioms, okay? So there are two cases. Either this ideal consists of the zero element only, or it contains at least one non-zero element, okay? If it has, if it consists of the zero element only, then you can represent I in this form, where k is equal to n. So, well, if you multiply n by any element of Zn, you will get 0, okay? Because n is the 0. Okay, so now we consider the case where x, where we have a non-zero element inside of I. And we want to represent I in this form. We want to show that the whole I consists of all these elements. So in order to do that, we need to find this element k. So I want to define this element k. How to define this element k? So Zn consists of the elements 0, 1, etc., n minus 1. So there is 0, and all other elements are positive integers between 1 and n minus 1. So if I consists a non-zero element, then it also consists the smallest possible non-zero element. So let's define the smallest non-zero element of I by k. Okay?
Yeah, okay.
So now I want to show you that every element of I is of this form. But what does it mean that you have k times Zn? It means that every element of I is representable as a product k times something from Zn. So I want to show you that, well, basically this means that I need to show you that every element h of I is divisible by k. So it can be represented as k times something. Okay. So, well, let's take an arbitrary element h from I, and let's divide as an integer number h by k with remainder. So this is a division with remainder. Then what was here is just some explanation saying that then the remainder must also be inside I. So let's skip this for a while. So if remainder is inside I, then by definition of the division, R must be strictly smaller than K. And K was chosen as the smallest non-zero element of I. So since R is smaller and also belongs to I, then R must be 0. And this proves that H is divisible by K. So every element H of I is of the form K times something. Okay?
Okay.
So the only thing I need to explain here is this part, why R is also inside I. And here I use axioms of I. What do I have? I have well, from here, H belongs to I. From here, K belongs to I. Q is an arbitrary integer. By the definition of the ideal, if I multiply an element from an ideal by any element of the ring, the product stays inside the ideal. So QK is also inside I. And then R is a difference between H and QK. And since I is an abelian group because it's an ideal, then the difference is also inside the I. So that's why the remainder is inside the I.
Can't we just prove it by saying that we have H from I and K from I, therefore H is from Zn and K from Zn, and therefore if we have some like elements between K and H, therefore R has to be also in I and in Zn.
Well, all these elements are in Zn by default because all the operations happen there. I just don't understand the reason why R must be inside I. Could you repeat your reason?
Yeah, I get it now. Maybe it's not that clear from my proof.
So, I mean, it's not hard. What I'm doing here, it's not hard. It's more or less obvious, but I just want to be precise. I just want to explain precisely in which place which axiom is used.
So, do we get like the fact that R is in I by saying that R is equal to 0?
No, okay, let me write it here. Because of this equality, we have R is equal H minus QK. So this guy is inside the ideal, and this guy is inside the ideal, and Q is inside of Z. Then the product is inside of the ideal, and then the whole difference is inside of the ideal.
Okay, that's just by the definition of I.
Yeah, that's by the definition of I.
Oh, and therefore, if R is also in I, it has to be 0 because
yeah, it's smaller than K.
Yeah. Okay.
Yeah, exactly. Well, strictly speaking, well, I didn't prove the claim here because I have proven that K, well, I belongs to K times Zn. So here the left to right inclusion is proven. But, well, right to left inclusion is more or less obvious. So each element of the form K times Q belongs to I by the definition of I. So that was the part that I didn't pronounce here, but I believe it's clear. Are there any other questions? Or probably you have?
Actually, yes, I have one more one question. That's so when you were talking about homomorphisms,
okay,
there was actually like at the top.
Oh, okay. The kernels and
yes, the kernels and there was a claim that a kernel is an ideal of R.
Yeah.
Why?
Okay. You see, how do you prove that something is an ideal of a ring? You need to show that this something is an abelian subgroup with respect to addition. And then you need to check this second axiom that if you multiply everything from the kernel by an element of the ring, you will stay inside the kernel. Okay?
Yep.
Well, the first claim, in order to prove the first claim, I just reduced the problem to the same problem for the homomorphism of abelian groups. Well, if you forget the multiplication from R and S, then this becomes a homomorphism of abelian groups. And the kernel of, well, for the homomorphism of abelian groups is a subgroup. So this is how I prove that the kernel, well, is a subgroup inside R plus. Is this part clear?
Yes. So basically, by definition, right?
Yeah. So yeah, here, but yeah, this part was by definition, but the part we're saying that the kernel is a subgroup, well, it's something requiring verification of the properties of the subgroup, but we already did this verification when we dealt with groups.
Wait, so we can say that because we know that the kernel is a subgroup of R.
Yeah, yeah.
Okay.
Yeah, because the kernel of the homomorphism of groups is a subgroup. So here we use this red part. So the next part is to show that if you take an element from the kernel and an arbitrary element of the ring R, their product in any direction will be inside the kernel. And I proved this for the first case. And the second case is exactly the same. So how do I do this? Well, how do you prove that something is inside the kernel? By definition, something is inside the kernel if and only if you apply phi to this element and the result will be 0. So if I compute this expression and the result will be 0, then xy is inside the kernel by definition. So how do I do this? Well, here I use the property that phi is a homomorphism. And here I use the property that x is inside the kernel. So phi of x is 0. So now I need to prove that if I multiply 0 by any element of the ring, I will get 0. And here is a separate proof for this specific claim. So if you take an arbitrary element S of the ring S and multiply it by 0, it's the same as this, because 0 plus 0 must be 0. And then when you expand, this expression, you will get S times 0 plus S times 0. And now you can cancel this out, and the 0 is left on the left-hand side, and on the right-hand side, S times 0. And this is how you prove that S times 0 is 0.
Okay.
Okay. Are there any other questions?
Sorry, can you please just show the definition of rings?
Yeah.
Firstly.
Just give me a second. Here is the definition of rings, including all. Okay, let's do it like this. Yeah. So now everything should be inside your side of view. So it's a set with.
I just didn't see like the point where def is. I saw like maybe there's something more.
Oh, I see. So this is the whole definition. And
okay.
These two parts define specific types of rings, like commutative rings or even fields.
Oh, like, by the way, I wanted to ask, so for example, we have all our 4 axioms of a ring, and we have
yeah, and additionally, yeah. So here, and here.
For
Yeah,
example,
so
what for sorry, can I ask?
Yeah.
For example, what if I have also 6th and 7th? Is it enough for like what's it called?
Oh, so suppose you have all the axioms but the 5th one.
Yeah.
Then it's called a skew field. Well, if you have a ring which is not commutative, but every non-zero element is invertible and the identity is not equal to 0, then this ring is called a skew field.
So it's not really a field.
No, it's not commutative field. There is a notion of a non-commutative field, and the term for this notion is a skew field.
Okay, thank you very much.
There is such an object, but I don't want to deal with them. It's not that important for us. For example, quaternions form this kind of objects. Are there any other questions? Okay, then, guys, thank you for being here. I hope you will come to the next lecture. Bye.
Goodbye.
Thank you. Goodbye.
Whoa.
Jeez.